This video is part 1 in a series about using simple continued fractions to decompose Pythagorean primes. We'll define our problem statement, and we'll discuss how to determine which prime numbers are Pythagorean. Let's get started. For background, we'll just do a quick review of the Pythagorean theorem. If we have a right triangle and label the sides a, b, and c, the lengths of the sides obey the theorem, which says that a squared plus b squared equals c squared. When we are decomposing a Pythagorean prime, the Pythagorean prime itself is given. The hypotenuse c equals the square root of n sub p, the Pythagorean prime that we are decomposing. What we want to find are the two integers a and b that satisfy a squared plus b squared equals c squared, which equals n sub p, the Pythagorean prime. As a short aside, since we are looking for integer solutions to the equation is a Diophantine equation. In part 2, we'll see how to do this using simple continued fractions. That's our problem statement. Now let's talk about which prime numbers are Pythagorean. Not all of them are. There are criteria from what is called Fermat's theorem on the sum of two squares. What the theorem says is prime numbers of the form 4n plus 1, where n is a non-negative integer, can be expressed as the sum of two square integers. Numbers of the form 4n plus 1 include 1, 5, 9, 13, 17, 21, and so forth. They are half of the positive odd numbers. Some of the numbers in this infinite set are prime. These, for example, are prime. These and all the other ones we'd encounter if we kept going are Pythagorean primes. Fermat's theorem also says that prime numbers of the form 4n plus 3 cannot be expressed as the sum of two squares. Numbers of this form include 3, 7, 11, 15, 19, 23, and 27, and so forth. This is the other half of the positive odd numbers. Some of these are prime too. For example, these are prime. However, the theorem tells us that they cannot be expressed as the sum of two squares. For these primes, there's no solution to the equation we are solving. These primes are not Pythagorean. Incidentally, sometimes instead of saying the form is 4n plus 1, what is said is the numbers are congruent to 1 mod 4. I'm not going to explain this in this video except to say that these are two ways of saying the same thing. Also, instead of saying the numbers are of the form 4n plus 3, it can be said they are congruent to 3 mod 4. It's two ways of saying the same thing. These two forms, 4n plus 1 and 4n plus 3, cover the positive odd numbers and therefore all the odd primes. But there is one even prime, 2. What about 2? Do you think it is a Pythagorean prime? Besides being prime, 2 can be expressed as the sum of two square integers, so you might think it's Pythagorean. However, it is not. The reason is, to be considered Pythagorean, you have to be able to express the prime number itself and also its square as the sum of two squares. We can express 2 as the sum of squares, but not 2 squared. So, 2 is not considered Pythagorean. To close out the discussion about which primes are Pythagorean, we'll make a table of the first handful of prime numbers. We have a column for x, which will have some prime numbers. The second column indicates whether the prime is Pythagorean, and the next columns will have values for a squared plus b squared equals x when a and b exist, and a squared plus b squared equals x squared when a and b exist. I'll fill in some of the first prime numbers. Could you fill in this column to indicate whether the prime is Pythagorean? Review what we just discussed if necessary. Here is the answer. Take your time and look it over. Does it make sense to you? Here are the values for the remaining two columns. Notice that 2 can be expressed as the sum of two squares, but 2 squared cannot. But the Pythagorean primes have values in both of these columns. All Pythagorean primes can be expressed as the sum of two squares, and so can the Pythagorean prime squared. What we'll do in the next video is find a and b that would go in this column, but for larger numbers. In particular, we'll find a and b for 115,601 and 173,189. In this video, we wrote a problem statement for decomposing Pythagorean primes and talked about which prime numbers are Pythagorean. That's all for now.